Okay, Chapter 6, Section 3, Length of Plane Curves. This is referring to the idea that we can measure the length of a curve. So here is a curve, okay, and the question is, how long is that curve? Well, we'd have to think a little bit about that and how we're going to measure it. What we might do is try to estimate the length. Instead of by measuring it directly, we say, well, let's imagine we have a series of points along the x-axis, little intervals, and we measure the length of this section, length of this section, the length of this section as straight lines. And then we add all those straight line sections together and we get an estimate of the length of the curve. And you could say, well, depending on how far apart you put these sections, if we put them a little bit closer together, something like this, our sampling points, then we get shorter straight line segments, and while they're still straight line segments, you can see as I draw them in roughly here, they are closer, so our estimate gets better. You can probably see the direction we're going here. If we take the idea of Riemann sums and calculus, and we can see that at the limit we have an infinite number of points along this segment of curve, and we estimate an infinite number of these little straight lines, and then as a limit we approach the actual length of this segment of the curve. Well, let's make this more concrete, and let's say that I wanted to calculate the volume of this projectile bullet-look shape from 0, and we'll call this 4 to 4. For I want to calculate this. So we set up the problem. Okay. We want to go from 0 to 4. Alright. We see the projectile, the thickness of the disk that we'll be using are in the x direction. So we know this is going to be dx. Therefore our equation must be in terms of x. We come up here and say, well, this is the equation for the outside of the radius. In other words, we pick this point right here, just arbitrary point, and we go up and say, what's the radius at this point? Well, it's going to be this defined by this function line here. What is this function? Uh-oh, time to go get Mom. Okay then, let's take a look at a parametrically defined function where we have some kind of equation for the x value and the y value, and we're going to plot them out here, and the curve looks something like this, for instance. And let's imagine that we have, you know, a point here and a point here. That's one value and that's another value. And we're going to say, well, what is the length of the curve in between these 2 points? And to start with, we're going to make a very simple assumption. We're just going to say, well, let's just estimate it with a straight line, like that right there. Okay, so we've got these 2 points, okay, and let's say this is, you know, point 1, point 2 on this axis, and so it corresponds over here. We got like this, and so we know what the values of x and y are. This is going to be x1, and this is x2, and this is y1 and y2. And the question is then, how long is that straight line? Well, that's just the hypotenuse of a right triangle, so that we can see that it's going to be x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Take the square root of that, and that's going to be that length. If we repeated this all along the curve, making point 1 and point 2 closer and closer together, that's that process of estimating the curve. But for right now, just realize that this hypotenuse is an estimate of one of our little straight line segments. Now, what we need to do is go from this very straightforward idea of a series of hypotenuses that can be added up to a definition in calculus of how we would actually calculate the length of this segment of curve. Of course, you can just skip forward to the definition and memorize that, but I'm going to spend just a second here to try to develop where that definition comes from. Well, first off, remember this is parametric representation, so that x and y's have functions that define what they are. So x is equal to a function of, and let's make it t, and the reason t is often picked here is because it's sort of an easy way to think about like time. At time 1, 2, 3, 4, x is at position 1, 2, 3, 4. And in the same way, y has some other function, g of t, and so these t's match up. So at time 5, we could calculate where x is. Time 5, we calculate where y is, and then we could go over here, and if this point corresponds to time 5, that's the value of x, and that's the value of y, and that's where we are in xy space. Okay? So let's, for a second, forget this curve and go over here and draw a curve where we're going to have an x value, and here's a t value. And now this, of course, is not directly related here, but you can see that x is increasing over time. So let's say that it looks like, I don't know what it looks like. It looks like something. And so here is t at time 1, and here's t at time 2. And there's our positions in the x values at those two times. Now, there is a slope that takes place on average between these two time points. And so that's just going to be f of t2 minus f of t1 divided by the change in t. And that's going to be equal to, now what can we think about that being equal to? Well, it's kind of the average slope, okay, something like that. So we can sort of imagine that as a limit, this is actually equal to a slope at some time in this interval. This is the mean value theorem here. So there is some value of t, we'll call it t asterisk, in the middle here, that has a slope exactly equal to that. Now remember the mean value theorem? So we get this sort of thing going on. Alright, but we can rearrange this and say that the slope at that point, t asterisk, times delta t is equal to ft2 minus ft1. Okay, but of course that is just x2 minus x1, right? And this is what we had in our equation up here. So therefore we could also write a similar equation, g prime at some point t, delta t is equal to y2 minus y1. Now there's a little bit of arm waving here about the t values and things like this, but as a limit, as our distance between t's gets smaller and smaller, these equations should work. Now the question is, how do we put this all together?